we have draw the Lewis structure for methanol, okay? And then we have, based on the structure, predict the HCH bond angle, and then we also want to predict the HOC bond angle, and want to explain our reasoning for both. So first, we have Lewis for methanol, which is H3COH. So now methanol is a little bit tricky because we have to know that we're adding a hydroxide group. The reason why I say that is because the best thing to start with is just drawing the methane. Okay, I know that we're adding extra steps, but if we just jumped right to drawing the methanol, we would most likely end up confusing ourselves. Okay, so with that being said, we have CH4 for methane. Okay, that is 4 4 valence electrons for carbon and 1 each from hydrogen. So we are working with 8 electrons total. This is for methane, and we have it like this. Okay, and this is balanced out. This is the Lewis dot diagram for CH4 methane. Okay, now an alcohol, just like how we have for methanol, is when a hydroxide group gets added. It replaces a hydrogen. What is a hydroxide group? This is known as the OH minus group. Okay, that is a hydroxide. So what it's gonna do here is that any of these hydrogens here gets replaced by an OH. So I'm actually going to copy this and paste it, because what we're going to do now is replace one of these with the hydroxide group. So right here, we're going to write OH. And you notice, bam, we actually have the Lewis for H3COH. It was just important we started with methane, so that way we wouldn't try to, make all the atoms go around the carbon, because that would just confuse us, which is why I like to first draw that structure first, specifically methane. For these type of questions, it is important that you understand the original hydrocarbons we're working with, so there is a little bit of familiarity with the naming and the IUPAC rules. That's how I was able to get here. So this right now is what we have for the Lewis structure, and make sure we add in our electrons, and we can actually verify to see if everything is correct. So first of all, how many electrons do we have total here? For methanol, we would have 3 electrons we can work with, plus 4 from the carbon, plus 6 from the oxygen, and then another one from hydrogen. So that's 4 plus 4 plus 6. We need 14. And if you count, we have 1, 2, 3, 4, 5 bonds. That's 10 already electrons. And then 2 pairs each on the oxygen. So this does indeed add up to 14. And if you compare the formal charges, hydrogen's net formal charge of 0 is when it just has 1 bond. Carbon is when it has 4 bonds, and oxygen is when it has 2 bonds and 2 lone pairs, which it does indeed. So this is actually balanced with the electrons, the octet rule, and the formal charges. This is the Lewis structure for methanol. Now the question is asking us, based on this structure, predict the HCH bond angle. Okay, so they're looking for like a bond angle of one of these. So in order to do that, we first need to understand what type of bond we're dealing with for both of these. Okay, so we're going to make each, the carbon and the oxygen, our quote-unquote central atom. Starting with the carbon, we have, it has 1, 2, 3, 4 bonding groups. Okay, well, 4 bonding pairs and 0 lone pairs. So that would be, we just write it as 4, 0. The electron geometry would be tetrahedral, and the molecular geometry, based on the fact that it's a 4-0 split, 4 bonding pairs, 0 lone pairs, it's also tetrahedral. The electron geometry is based on the total, which is just 4, which is why it stays with the name tetrahedral. And the molecular geometry breaks it down of like, okay, now which one of each do we have? So with that being said, we can now take a closer look at this. in regards to, just to make sure we have everything, tetrahedral molecular geometry looks kind of like this, where one is going into the page, one is going out of the page. But overall, all the angles that they have there is around 109.5 degrees. That is like, because it's a 3D structure, that is a perfect distance they can have from each other to where everyone is equally distanced from themselves. So when it asks the question, predict the HCH bond angle, that includes one of the HCH. So if I said this was H, this was H, and the carbon was in the middle, that would be the bond angle there. So for B, bond angle will be 109.5. Okay? And reasoning being because of the tetrahedral shape. Alright? For the molecular geometry specifically. Now if we look at the oxygen, this one's a little bit different. We have, let me just erase these so there's no confusion. We have 1, 2, most wrong color. We have 1, 2, 3, 4. So now with this, although we have a 4 total, so it's also going to be tetrahedral for the electron geometry, we have 2 bonds and 2 lone pairs. So although for the electron geometry it is tetrahedral, the molecular geometry is known as bent. And what this does is that if we drew it as well like the 3D structure, we kind of have the oxygen here and the 2 H's. Okay? And what's happening here, the reason why it's called bent, is that not only does it try to mimic the tetrahedral shape, but it really doesn't. What happens here is that because of the lone pairs, it kind of exerts angled force on it. So instead of it being that 109.5 like the other tetrahedral, it actually squishes it a little bit. So all we can say, we don't know the exact amount, but we can say that it's going to be less than 109.5. So for C, it's less than 109.5 because the molecular geometry is bent. We don't know the exact amount. It's not too drastic. We're not saying that it's a 1 degree. We just know that it's not exactly 109.5 because the lone pairs don't have like an even distribution split with the other atoms attached. They actually do exert a force where they kind of push things in a little bit closer. So that's what we're dealing with here. B, 109.5. C is just less than 109.5 for the bond angles based on the structure of their geometries. So let's see how we did. Exactly. So this is what they have here as well for methanol. And they say it has 4 bond pairs and lone pairs. So the electron geometry is tetrahedral with bond angles of 109.5 degrees. I would actually use molecular geometry because now we'll see if they got the right answer for the next part. So it has 4 electron groups, and that's what I was afraid of here. They based it off the electron geometry. It is tetrahedral as well for the electron geometry, but the bond angles, like I said, although it'd be close, it wouldn't be exactly 109.5. It'd be a little bit less. So the only thing I would say here is that technically what they're saying isn't wrong except for the bond angle part. If you were asked this question and you're given some choices and A said 109.5, B said less than 109.5, for the oxygen one, the most correct answer would be B. Because if this person had drawn the molecular geometry instead of referring to electron geometry, I think they would have noticed that the bond angles are just slightly less than 109.5. Because although the electron geometry is tetrahedral, the molecular geometry, as you can see here, from the 2 lone pairs and the 2 bonds, it is going to be bent. So, bent molecular geometry for COH means that it's less than 109.5, not 109.5 exact. So, with that being said, although everything else they did was fantastic, these are just the little things that can make you, for example, get the question wrong, because you just have to recognize that part when it comes to the molecular geometry. So question number 5.